In this video, we're going to have a look at some titrations involving dilutions, and we're going to have a look at the calculations that come from those types of titrations. And quite often, these examples involve the analysis of vinegar. So we're going to start off by looking at some of those examples now. So as I've mentioned, this is quite a common example for this type of titration, so it's important that you are familiar with this type of calculation and particularly applied to the analysis of vinegar. So it's important for that you know that the acid in vinegar is ethanoic acid. You would have learnt that at GCSE, and it's important that you know the formula of ethanoic acid as well. And that is CH3COOH, and you do need to know that off by heart. Ethanoic acid is an example of an organic acid. It is a weak acid. It's an acid in the sense that it dissociates in water or in solution to produce hydrogen ions, as you can see from the equation that I have just written. So those hydrogen ions in solution make it an acid, but it only partially dissociates, and that's what makes it a weak acid, a definition that we have learnt earlier in the topic. So you can see that's the equation for the dissociation above. And you can see that the arrow that I've used is a reversible arrow, which indicates that not all of the ethanoic acid molecules will dissociate into the ions. Some will stay as the molecule itself, and I suppose this is reversible in the sense that some of the ions that have dissociated will then bond back together again to form the whole molecule. So ethanoic acid is a weak acid in the sense that it doesn't produce as many hydrogen ions per volume of solution. So there's a lower concentration of hydrogen ions in your solution, and that makes it a weak acid. So all of the examples involving the analysis of vinegar will involve it being titrated against a strong base. Why is that? Well, we know that weak acid versus weak base titrations don't really work. We'd have to use an electronic pH meter, and so therefore we have to titrate it against a strong base, since ethanoic acid is a weak acid. So in general, our solution of vinegar will be too concentrated to start with, and that's why we have to dilute it. And it'll be diluted either from 10 centimetres cubed of the original solution to 250 centimetres cubed, or from 25 centimetres cubed to 250 centimetres cubed. You can see the final volume is generally always 250 centimetres cubed, and that's because that tends to be the standard volume of our volumetric flasks. So the dilution factor will be really important at the end of your calculation, and that will allow you to calculate the initial concentration of the acid before you dilute it. And the dilution factor is calculated by taking the total volume of the diluted solution and dividing it by the volume of the undiluted or the original solution. So for example, if we take that first dilution mentioned there, 10 centimetres cubed of the original solution being diluted to 250 centimetres cubed, well, the total volume of my diluted solution is 250 centimetres cubed. That's divided by the volume of the undiluted or the original solution, and that is 10 centimetres cubed. 250 divided by 10 is 25. So we've diluted it by a factor of 25. It is 25 times more dilute than the original solution. And just check your units that those cancel out. So you can see I've got centimetres cubed on the top and the bottom half of my equation. If one of those was given to you in decimetres cubed, you would need to convert it. Okay, so you would make that up in your volumetric flask. So that would be made up to 250 centimetres cubed. And from that, you would take your 25 centimetres cubed of your solution, and that would be done using a pipette, and that would then go into your conical flask. So no, that's a very messy diagram, but you would get your diluted solution from your volumetric flask, pipette out 25 centimetres cubed, and put that in your conical flask to then be titrated against your strong base. So the strong base will be the one that we know the concentration of. So generally it will go in the burette, because generally our standard solution goes into our burette, the one we know the concentration of. So we rinse it and fill it, the burette, with our strong base, such as sodium hydroxide or potassium hydroxide and so on. Then we come on to our choice of indicator, and in this case it must be phenolphthalein. Why is that? Well, it's because this is a titration of a weak acid versus a strong base. So as we discussed last week, with strong acid versus strong base, you can use either methyl orange or phenolphthalein. With a weak base versus a strong acid, it must be methyl orange. And with a weak acid versus a strong base, it must be phenolphthalein. Methyl orange will not work for this type of titration. So in that sense, you can learn that that would be always your indicator of choice. But you also know that for weak acid versus strong base, the indicator of choice is phenolphthalein. Now, you obviously have to double check which solution has been added where, but because we're trying to find out the concentration of the vinegar of our ethanoic acid, that is in our conical flask because we don't know the concentration of it. And the solution that fills our burette is our strong base, for example, sodium hydroxide. So in that sense, we can also predict the colour change in that if our acid is in the conical flask, phenolphthalein will be colourless to start with, and then it will change to pink on the addition of our base. So colourless because phenolphthalein is colourless in acid, which is in the conical flask, and changing to pink because we're adding base, and phenolphthalein is pink in alkali solution. So down at the bottom of page 29, you have a diagram, a simple diagram to show this dilution and titration. So you can see you take your vinegar, maybe take a 25 centimetre cubed sample in this case, make it up to the 250 centimetres cube marked using your volumetric flask. Then take a 25 centimetre cube sample from that using your pipette, and add 5 drops of indicator, and then titrate against your strong base from the burette. In this case, the dilution factor, remember, it's the total volume of your diluted solution over the original volume or the undiluted volume. So in this case, our dilution factor is going to be times by 10. So that means the initial vinegar, the undiluted vinegar, is 10 times more concentrated than the diluted. So it will have a concentration that is 10 times higher than the diluted vinegar. So let's look at this worked example together. In this question, we are told that we have a sample of Sarson's vinegar, that's just a brand of vinegar. It was diluted by pipetting 10 centimetres cubed. I would highlight that because we're going to need that. Of the original vinegar into 250 centimetres cubed volumetric flask, and making up the volume to 250 centimetres cubed using deionized water. So even at this early stage, it would be worthwhile working out your dilution factor to remember to factor that in at the end of your calculation. So again, remember it's the final volume, the total volume of your diluted vinegar divided by the original volume of the undiluted vinegar. And 250 centimetres cubed divided by 10 centimetres cubed is 25. So our dilution factor is times by 25. So our original Sarson's vinegar is 25 times more concentrated than the solution I will be using for my titration, because it is the diluted vinegar that I use for my titration. So in our titration, we take 25 centimetres cubed sample of our diluted vinegar, and that's titrated against 0.05 sodium hydroxide. That's our strong base, and the indicator is phenolphthalein. The average titer was found to be 18.5 centimetres cubed, and remember that is of your strong base, that's of whatever is in your burette, and that is going to be our sodium hydroxide. And the equations given to you there, the equation for the titration reaction, the neutralization reaction, but that's not always given to you, so you need to be able to write those equations from memory. So you can see there you've got your ethanoic acid, CH3COOH, reacting with sodium hydroxide to produce sodium ethanoate, that's our salt, plus water. Because remember, an acid will react with an alkali to produce salt plus water, or acid plus metal hydroxide gives salt plus water. And the name of our salt is sodium ethanoate. And you can see it's written a little different than some other salts. If you think of like sodium chloride, which you would form from sodium hydroxide and hydrochloric acid, say, that has the metal coming first. But with our organic salts, it's actually the formula of the what we call carboxylate ion. So in this example, we have our ethanoate ion, the CH3COO minus, and then our sodium afterwards, which would be Na plus. So you've got a bit of space underneath your equation there, and what I would use that to do is draw a basic diagram of what is happening, a bit like what we saw on the previous page. So we're going to start with our sample of our original vinegar. What do we do with that? Well, we take 10 centimetres cubed of it, as told in the question, and we put it into a volumetric flask and make it up to 250 centimetres cubed. So that will leave us with our diluted vinegar. What we're going to do with that is we're going to take 25 centimetres cubed of it and we place it in our conical flask. So 25 centimetres cubed will be pipetted out and put in our conical flask because it's our unknown solution. And just to help you keep a track of which is your diluted vinegar, which is your original undiluted vinegar, I would write underneath your conical flask that this is our diluted vinegar that we're using in the titration. So what do we then do with that conical flask? Well, we titrate it against our standard sodium hydroxide. So we're told in our question that it is 0.05 molar sodium hydroxide. And that we need a titer of 18.5 centimetres cubed to neutralise the acid in the conical flask. So I think sometimes these diagrams are helpful to draw. Now, how the questions are asked to you can vary from time to time. Sometimes it's just a case of calculate the concentration of the ethanoic acid, and that is that. And so these diagrams help you then structure your calculation. But sometimes they are structured, but in that sense, sometimes they're different. Sometimes it will get you to work out the concentration of the diluted vinegar and then essentially use your dilution factor to calculate the concentration in the original vinegar. Other times it will get you to work with moles all the way and then finally work out the concentration just of your original vinegar. So having a diagram like this will help you structure your calculation, and then you can kind of adapt it depending on whether the headings talk about moles all the way through or whether they get you to calculate the concentration of the diluted vinegar first and then use your dilution factor. So let's have a go at this calculation. So it says, using the following headings, calculate the concentration of the ethanoic acid in the vinegar in grams per decimeter cubed. And it's worthwhile sort of noting what concentration units do they ask me for the concentration in. So the first thing is, and as we talked about earlier in the week, our titration calculations always start with the titer, essentially, because that gives us then our volume of the standard solution, and so from that we can work out number of moles, and from that then we can bring that to anywhere else in our equation. So the titer of our sodium hydroxide is 18.5 centimetres cubed, so that is the volume that I have used to neutralise the diluted vinegar. It's worth at this stage converting that to decimeters cubed because that's what I'll need for my equation. So what we want to do is use our equation N equals CV. Our concentration, we're told in the question, is 0.05 moles per decimeter cubed, or 0.05 molar. And that's times by the volume, which is 0.0185 decimeters cubed. So try and type this into your calculator as you go along, and that should give you 9.25 times 10 to the minus 4 moles. And that's in our sodium hydroxide used. Next part asks us to work out the moles of ethanoic acid in the conical flask. Well, in order to work that out, we need to use our equation for the reaction, and it is written above. So what I've done is just written the left-hand side of the equation, and that's all we really need. So we know that 9.25 times 10 to the minus 4 moles of sodium hydroxide has reacted. So how many moles of ethanoic acid were there to react with it? Well, we work that out by our stoichiometric ratio, or our balancing number ratio, which is 1 to 1. So obviously we have exactly the same number of moles. We have 9.25 times 10 to the minus 4 moles of our ethanoic acid in our diluted vinegar in the conical flask. So the next part of the question asks me to work out the concentration of ethanoic acid in the diluted vinegar solution in moles per decimeter cubed. So remember that our conical flask contained diluted vinegar, so we can work out the concentration from that. So we know that in our conical flask, we have 9.25 times 10 to the minus 4 moles. We know that that is in 25 centimetres cubed because we pipetted 25 centimetres cubed into our conical flask if you look up at our diagram above. So there's 9.25 times 10 to the minus 4 moles in 25 centimetres cubed. And so we use our equation C equals N over V, concentration equals number of moles divided by volume. So that's going to be 9.25 times 10 to the minus 4 moles from part B, divided by our volume in the conical flask, which is 0.025 decimeters cubed. Remember, we must convert centimeters cubed into decimeters cubed. Put that into your calculator and you get that the concentration of diluted vinegar is 0.037 moles per decimeter cubed. The next part of the question asks for the concentration of ethanoic acid in the original vinegar solution in moles per decimeter cubed. And here's where we need to think of our dilution factor, which we worked out up at the top of the page. So if you remember back to the start of the question, we were told that we took 10 centimetres cubed. Sorry, it won't let me start right beside that. So 10 centimetres cubed of our original vinegar, and we diluted that to 250 centimetres cubed. So we worked out at the top of the page that our dilution factor was equal to times by 25. So the original vinegar is 25 times more concentrated than the diluted vinegar. So if you're wondering which way round to do this calculation, do I times it by 25? Do I divide it by 25? Well, just think in your head, the original vinegar is going to be more concentrated. It's going to have a higher concentration than the diluted. So if you wanted to put that in the form of an equation, it would be the original concentration is the concentration of the diluted vinegar times by your dilution factor. And again, think about this. Does my answer make sense? Should it be getting bigger or should it be getting smaller? So the concentration of our diluted vinegar or ethanoic acid within the diluted vinegar is 0.037 multiplied by my dilution factor, which is times by 25. Which should give you 0.925 moles per decimeter cubed. So that's the concentration of my original vinegar. And finally, the question asks me to work out the concentration of ethanoic acid in grams per decimeter cubed. And this is more what we were doing at the start of the topic, looking at different units that we can use for concentration. And really, we're converting here from moles per decimeter cubed into grams per decimeter cubed. In other words, moles to mass. How do we do that? Well, we use our equation mass equals N times RFM. The RFM that we're working out is that of ethanoic acid. The formula again is CH3COOH. So that's going to be 12 from your carbon plus 3 essentially from your H3 plus 12 plus 2 oxygens, 2 times 16 plus 1 for your final hydrogen, or you can work out how many of each you have, so that would be 2 carbons, 4 hydrogens and 2 oxygens. Either way, that should give you an RFM of 60, and that will be something that you almost learn off by heart by the time you do all of these calculations, if they ask you for your concentration in grams per decimeter cubed. So your final answer is going to be mass equals N times RFM, your number of moles is 0.925 from part D, and your RFM is 60. Because remember, we've got the same volume here, it's per decimeter cubed, so I can just use this equation, mass equals N times RFM. That should give you a mass of 55.5 grams, and so that means our concentration is 55.5 grams per decimeter cubed. So in this question, we were able to work out the concentration of ethanoic acid in our original vinegar sample. Again, it is just basic moles calculations, but it's just being careful each step of the way about which stage you're at. Are you talking about the diluted? Are you talking about undiluted? What's your dilution factor? What's your ratio in your equation? And so on. So just be really careful with each step. So I want you to skip ahead to page 34. We will come back to that practical when we are able to do so. In the meantime, you can watch Miss Stewart carry out this practical on the SIA website, and I've given you the link to that practical, and that is of the analysis of vinegar, and it's very similar to the one that's stated in your notes there, but we'll just skip past that for now. What I want you to do, just so that you have practice of one of these on your own, is I want you to try just question 1, and we'll come back to the rest of the questions next week, but can you give a go at exercise 6, question 1? Just while we've done a bit of practice of this, see if you can try one by yourself. I would suggest that you draw yourself a little diagram to help you with this. And again, your calculations are structured in such a way that they will ask you to calculate the concentration of your diluted and then your undiluted. So it's worthwhile maybe working out your dilution factor at the start. So give this a go, pause the video now, and then I'm going to go through it afterwards just to make sure that you understand this okay. So pause the video now and give this a go, and then check the rest of the video for the answer. So let's have a quick look at this calculation. So we're told that analysis of vinegar solution was carried out using the following procedure. We're told that 25 centimetres cubed of undiluted vinegar was transferred and made up to 250 centimetres cubed. So already at this point I would be getting ahead of the game and working out my dilution factor. So that's going to be 250 centimetres cubed divided by 25 centimetres cubed is equal to times by 10. So the dilution factor is times by 10. Then we're told that 25 centimetres cubed portions of the diluted vinegar was put into conical flasks, 3 separate to do your rough and 2 accurate, and that tells us the volume that is in the conical flask. You're told that indicator is added to each flask, and that is titrated against 0.1 molar sodium hydroxide solution until the end point is reached, until you get your colour change, and your results are in the table. Now, in order to do this calculation, we will have to work out what our average titer is. So in order to do that, we're going to need to work out the titers of our first accurate and second accurate. How you do that, remember, is by taking your initial burette reading away from your final burette reading. So you can see with the rough titration, the titer was calculated by doing 21.7 minus 0, which is obviously 21.7. With the first accurate titration, you're doing 43.1 minus 21.7, which works out as 21.4. So you can see that's less than the rough titration, which it should be. And then for the second accurate, you're doing 21.3 minus 0, which is obviously 21.3. So let's have a look at the questions, and we've actually done part C, but we'll come back to that in a second. Part A asks you to name a suitable indicator for this titration and state the colour at the end point. Well, remember, because vinegar contains ethanoic acid, which is a weak acid, and we're doing this against sodium hydroxide, which is a strong base, then we've got to use phenolphthalein. So a weak acid versus strong base titration is always phenolphthalein. And your colour change, remember, is your conical flask colour to your burette colour. What have we got in our conical flask? Well, we've got acid. So what colour is phenolphthalein in acid? It's colourless. And then we're adding sodium hydroxide, so it will change to pink. The next question asks you to write the equation for the reaction between vinegar and sodium hydroxide. Well, what you need to remember is that the acid in vinegar is ethanoic acid, and that has the formula CH3COOH, so you do need to know that formula. That's reacting with sodium hydroxide with a formula of NaOH. An acid and an alkali react together to give a salt plus water. So what's the name of my salt going to be? Well, it's going to be sodium ethanoate, which has the formula CH3COONA. And then we also get water, and that obviously has the formula H2O. If you have a look at that equation, it's balanced. Basically, the hydrogen from the end of your ethanoic acid is reacting with the hydroxide ion from the sodium hydroxide, and that's producing water. And as a result, the sodium ion is replacing the hydrogen ion that was initially with the ethanoic acid. So that's where it goes in there. So part C then asks us to complete the results table, which we've already done, and calculate the average titer. I'm just going to do this off to the side, but hopefully you've done it on file paper to give yourself a wee bit more room. Remember, your average titer is calculated from your two accurate titrations, so your 21.4 and your 21.3. You do not include the rough. So you're simply taking the average of 21.4 and 21.3, so that add those two together and divide by 2, and that should give you 21.35 centimetres cubed. Let me just carry this on at the bottom of the page. So part D then asks us to use the average titer to calculate the number of moles of sodium hydroxide used in the titration. Well, we're going to use our equation N equals CV, because we know from our question the concentration of sodium hydroxide is 0.1 moles per decimeter cubed. And our volume is our average titer, which is 21.35 centimetres cubed. You need to convert that into decimetres cubed by dividing by 1,000, and that gives you 0.02135 decimetres cubed. So put that into your calculation, 0.02135 decimetres cubed, and that gets you a number of moles of 2.135 times 10 to the minus 3 moles, or 0.002135. Part E then is really our titration calculation, and there's a couple of steps here where that was maybe in 2 or 3 steps in the previous question, but it asks us to calculate the concentration of ethanoic acid in the diluted vinegar. So what I need to do is think about my titration. I've got sodium hydroxide reacting with ethanoic acid. I know that I've reacted 2.135 times 10 to the minus 3 moles of my sodium hydroxide. So I can work out how many moles of ethanoic acid has reacted by using my balancing number ratio. That's just 1 to 1. So I know that 2.135 times 10 to the minus 3 moles of my ethanoic acid reacted. Let's have a think then what volume that was in. Well, this was in your conical flask. So that's 2.135 times 10 to the minus 3 moles in your conical flask, which was 25 centimetres cubed of the solution. And so we work out our concentration of the diluted vinegar by using the equation C equals N over V. The number of moles is 2.135 times 10 to the minus 3. Our volume is 25 centimetres cubed, but we need to convert that into decimetres cubed. And so that is 0.025 decimetres cubed. And if you put that into your calculator, it should give you 0.0854 moles per decimetre cubed. And that's of your diluted vinegar. And finally, in part F, it asks you to work out the concentration of the ethanoic acid in the undiluted vinegar. And that's where we need to take into account our dilution factor. So we know that the concentration of the diluted vinegar is 0.0854. And earlier on, we worked out that our dilution factor was times by 10, because we took 25 centimetres cubed of our initial vinegar and we made that up to 250 centimetres cubed. So really, when you're working out the concentration of your undiluted, it's really the diluted times by your dilution factor. So if you wanted to abbreviate it, it's the concentration of your diluted volume or your diluted sample times by the dilution factor. So our diluted concentration was 0.0854 moles per decimeter cubed times by the dilution factor, which is times by 10. And that gives us a concentration of 0.854 moles per decimeter cubed. And remember, have a think, have you done this the right way round? Yes, you're multiplying by the dilution factor because your concentrated, your undiluted vinegar is obviously of a higher concentration than your diluted vinegar. So your final answer should be 0.854 moles per decimeter cubed. So as I said, we'll come back to question 2 onwards next week. I'll give you a bit of time in your class time to work on those.